Thank you very much, Lena, and thank you, Björn, and everybody for inviting me to this conference. And I must say I learn a lot because music is a special world, and we had the pleasure this morning of having people talk to us that really understand the background of music and how it's generated. And so I've learned a lot, and I really enjoyed it. So what I thought I'll be doing, given that the title I had was Music and Brain Development, I was going to show you really some preliminary new results that we have from our studies and sort of try to put them into the context of this conference. And of course, you will see a lot of imaging, but you will also sort of hear hypotheses. And I'm asking you to give me feedback after my talk to if you think I'm completely off with my hypothesis or if there could be some truth to it. So when we think about brain development, which is in my title, then we think about a very complex process that starts very early on in human pregnancy, way before, of course, we deal with our preterm babies. Fortunately, even though I hear that half of the babies in this hospital are now in the NICU that are born somewhere between 22 and 24 weeks. But generally speaking, we can say that a lot of processes in the human brain development are, of course, highly genetically controlled and are probably not very environmentally sensitive. But then towards the early or late fetal period, there is some sensory-driven experience that starts to become relevant for the developmental steps that take place, which are essentially in this organizational phase of the third trimester. So while these are endogenously and non-sensory driven, they become sensory sensitive and maybe even sensory driven by the late third trimester or the early postnatal period. And then, of course, in infancy, we know that a lot of how children develop is environmentally driven and experience dependent. So the areas that are usually the basic mechanisms on which these environmentally or activity driven or sensory driven processes are involved is, for example, synaptogenesis and spinogenesis, but also axonal outgrowth and ingrowth into the cortical layers. And I will show you some indication that also myelination itself is absolutely activity driven. So clearly, if you change the environment dramatically, as we do for the preterm baby, in that period where we start to be sensory sensitive or sensory driven, we might actually change a lot of how the brain is going to be organized and how the brain architecture is both structural and functional. So this is just another way to illustrate this and give it also a little bit of an anatomical context. Generally, the sensory motor cortical systems develop prior to the prefrontal cortex, which is the more sort of attention, inhibition, emotional processing, socio-cognitive processing areas, and the parietal and the temporal, which is of course the language cortex, somewhere in between. So clearly there is inside the brain also a anatomically difference in the time course of development. So when we take the preterm brain, then people have used neuroimaging, but also EEG and other areas to actually show that the preterm brain really has altered connectivity, it has smaller volumes of cerebral cortex and subcortical gray and white matter, it has reduced sulcal complexity, it has altered thickness in cerebral cortex, and it probably also has altered function, not just by resting state functional MRI or by fMRI, but that's what we measure in our large neurodevelopmental outcome studies, that indeed they have various cognitive and sensory motor and sensorial differences compared to normal-born term-age children. So there are a lot of consequences, and Alison Abbott, who is a science writer in Nature, did a fairly interesting sort of state-of-the-art for everybody on the brain interrupted, as she called this, and she interviewed some of the researchers in that field. So when we think about it, then what evidence do we have about this interruption, and what could we do to not make this brain be interrupted? So these are just a few videos illustrating how the growth of the brain and the myelination that you see here illustrated on these T1 images. So here, very little at term, there is a myelination starting to go into the sensory motor cortex, and then the sort of myelination that goes on in the first 1,000 days of life, where with full myelination, intentionality and of movement is of course there, with a nice interplay also of what is expected of me. So this is clearly happening, and the underlying anatomical networks that undergo this myelination again have their specific trajectories, where you can see that the acoustic radiation, for example, starts somewhere in the fetal months and goes over the first few years of life to fully mature, and that is certainly one that we are particularly interested in if we try to intervene on a sensory-driven intervention with voices, music, which is the topic of today. So when we look at that from a neuroscience point of view, then there are very different systems, and some of these systems are mostly from the base of the brain to the cortex, so thalamocortical, and these are the networks that are responsible for many of the functioning, both the motor system as well as the more higher order cognitive functions are based in these basal ganglia thalamocortical loops, where there is the control of that. So they can actually, these thalamocortical input, they can be independent of cell intrinsic activity, but they can also be dependent on activity, and that really is how differently synapses can be modified, either activity independent or activity dependent. And recently there's been work done from California, where they illustrated in the rat model that if you activate by optogenetic ways of specifically activating one network, you then actually lead to the myelination of these axons. So clearly there's a direct link between, in some networks, between activity and myelination. So we did a very sort of early way of looking at that when we looked at our preterm babies' AEEG activity, so amplitude integrated EEG, and we looked not just at sort of the minimal or maximal amplitude, but we looked at the percent of time above threshold, so above a maximal threshold, so including bursts, so sort of what's the expression of the immature EEG of specific activity. And we looked at that in the first 72 hours of life of these preterm babies, and then correlated that with the brain growth, the subsequent brain growth towards term age. And you can see that the more active these children were in these first 72 hours, the better did their brain grow and the better did their brain myelinate. So clearly, within this situation of the preterm infant, activity seems to be a positive modulator of brain growth. So Charles Darwin in 1871 said, it is probable that the progenitors of man, either the males or the females or both sexes, before acquiring the power of expressing mutual love in articulate language, endeavored to charm each other with musical notes and rhythm. And I thought this was a very nice quote. So we would like to charm our babies with musical notes and rhythm. So let's see if we can actually bring some evidence to that. I looked up, what is there in the literature between music and language development, and came across some nice tables by Frontiers in Psychology review by Brandt, where he's comparing sort of what's happening in music development and what's happening in language development, and then sort of color-coded the ones that were occurring most likely at the similar time and the ones that were specific to one or the other. So for example, babies can discriminate sounds in all musical systems, and they can discriminate sounds in all language. Seems to be present quite early on. They discriminate non-native musical sounds to non-native speech sounds. And then maybe slightly different, they can very early on recognize rhythm across changes in tempo and pitch, maybe slightly later in language. At least he thinks that, but he puts that somewhere between 7 and 8 months. And we'll see if we go back to what we've seen this morning, we can probably challenge this view and put it much earlier in the developmental window. There's also very, of course, expressive language-specific things that are not the same as for music. It goes on, this table showing that we, for example, reach the pitch discrimination capacity of adult levels around 9 years of age. So music is clearly also something that develops over a long time period. So in that, of course, my interest is how does the immature newborn brain really function, and what's the difference between this sort of content full-term baby and the more alert preterm baby. Their brains don't look exactly the same. You see them here, even in the grayscale. You can appreciate that there are some morphological differences, even though there are completely non-lesioned brains. And how much function is present in these brains that still contain about 89% of water, right? So we can, of course, use many different methodology to look at functional neuroimaging. This is a list of them, and I'll show mostly data coming from functional magnetic resonance imaging. So I thought and I will, of course, focus on the theme of today, so auditory, voice, or music as a stimulation. I thought I would quickly go back to what is really functional imaging. So it's this bold signal-based imaging where we think there is neural activity that through neurovascular coupling leads to an increase of cerebral blood flow. It also leads to an extraction of oxygen because that's needed for the neuronal activity. But overall, it's a cerebral blood volume increase, which then leads to a difference between oxyhemoglobin and deoxyhemoglobin, which then leads to a change in the MR signal. So that is what we measure. So we measure a vascular effect of neuronal activity. We do not measure neuronal activity directly. But so there is also ways to measure neuronal activity directly by electrophysiology, or at least somewhat more directly. But just a few samples to show that there is early asymmetries even in structural imaging, where you can see that there is early leftwarded structural asymmetry in the planum temporale, where there is more early right-sided in the superior temporal lobe in preterm babies, which could link you to sort of language or voice perception functions of the left and the right hemisphere. There's clearly been shown that there is early left predominant ERP response as early as 3 months old babies, where you can also from the fMRI show that there is a language response in the auditory cortex with a left dominance. There's clearly sort of different ways to look at that: normal speech, filtered speech, hummed speech. So the more clear the stimuli, the more the response in the primary auditory cortex. When we looked at our data, so we wanted to see, so if we have full-term babies that listen to maternal speech or to another mother's speech, so a stranger person's speech, and we compare them with preterm infants at term that heard their mother's speech as well, much clearer, much longer, not attenuated through the womb. But I've also heard a lot of other stranger voices, nice voices, probably also with emotional timbre. At least that's what our nurses try to do. Can we see a difference? Does that change the maturation of the system? So if we do mother's voice versus silence, of course, we get this nice auditory cortex activation. We get also a nice auditory cortex activation when we do stranger's voice over silence. So clearly both groups of babies hear voices. They can do that. But then when we look in particular in the preterm, we see that the mother voice of the silence gives a huge response, much bigger than we have it in the full-term baby. And we also get a very much more intense response, including maybe even some more extended areas in the brain for the stranger voice versus silence. So then if we start to compare the two contrasts and we do stranger voice over mother's voice in the full term, there seems to be that the stranger voice actually in the full term can also sort of give some additional attention in the bilateral anterior superior temporal and insula and sensory cortex, whereas mother's voice over stranger did not show any significant results. So actually the other way around, like almost like the new voice was kind of more processed or more activated the brain than the one they knew. Preterm, no significant difference between mother and stranger. Nothing different. A little bit stranger voice over mother's voice with a little bit of a cingulate cortex, maybe attention network, and mother over stranger voice, a little bit of orbitofrontal cortex, which you could interpret as maybe some emotional processing. If we now look at the EEG results with the same kind of response, then we also see that the preterm actually has a stronger activation to language at term equivalent rate age than the full-term infant. So the same kind of result as in the fMRI, that the preterm baby has a bigger response than the full-term baby. So when we look at this, voice processing in preterms, full-term newborns, they have significant differences of processing between mother and stranger voice in localized areas, react to novelty, whereas the preterm infant has overall a stronger signal brain activation to all vocal stimuli than full-term. There's less difference between mother and stranger voice, but there is a clear link to potentially an emotional difference between mother and stranger. Effect of postnatal exposure. So they kind of learn that there are other people also, and they integrate them. So how about music? This is a nice painting from a Swiss painter, Albert Anker, who already recognized how important early music training is in small children. We know several studies have shown that music listening enhances cognitive recovery and mood, for example, after a middle artery stroke. And Daniela Perani and Paula Schiffa and Stefan Kölsch were the first ones to, with fMRI, show actually that newborns or a few days old babies were able to differentiate a music that they heard for a couple of times from a changed tune, so a modulated melody change, so a dissonance within the music, and they got a differentiated response, mainly though located entirely into the auditory cortex. So we were interested in how music training enhances functional connectivity in preterm newborns. And what the study looks like, I will quickly outline, because we read all the papers about Mozart helping babies to use less calories and have a more stable heart rate and so on. But then one Christmas, I listened to a TV reporting from Andreas Vollenweider, who is a Grammy Award musician in Switzerland, who plays the harp. And he's been involved in many projects, such as playing harp and music to prisoners in very bad prison environments and street children in areas, poor areas of South America. And so he had I thought, this is an interesting musician. So I contacted him and I said, would you be interested to play for preterm babies? He said, oh, what would that be? But we got him interested, and he came and he explored different instruments based on his knowledge. And so he came up with different instruments, and we tried out live playing harp, pungi, bells, and I just give you an example here. You see he's actively playing. You have this little guy who does his usual moving around. So I think it's a nice illustration of what we heard today also. It needs to be a really slow music, slow background, and then maybe some little sound melody variations that can relate to babies. And that's what we found out, that's what they were reacting to. So he went back and sort of composed 3 types of 8 minutes of music with this background, which actually sort of represents the level of voices mixed together. They were then designed to be pieces that would sort of let the baby fall asleep or wake up or be participant in the sound, like these little pungi that sort of invite us to what the melody is behind. So given the development that we already heard about by Pierre of when the auditory system becomes functional, we decided we would start with this auditory stimulation around 32 weeks, and then they were listening to these 8 minutes according to the nurse doing the developmental observation sheet, which is similar to the NIDCAP observation sheet, and deciding if her baby was ready to fall asleep or wake up or be wanting to interact. And then those were the moments that they choose to give them the little music over headphones. And then they had an evaluation. They had behavioral evaluations also and physiological evaluations, but I'll just report you the MRI that we did then at term age. So we had 3 groups of patients, so with music, without music, and the term group. And they underwent a fMRI protocol where there was first a resting state functional network acquisition, and then an fMRI where they used to hear silence, the background music, the original music, a transposed piece, so a key modulation, and a modulation of 40% faster, so a tempo modulation, just not of the background, of course, but of the actual melodic parts. So that's what that then gives. Let's see. That was a bit short, but let's see, in interest of time. And that one is the, sorry for that, the key transposed one. So that's what they were hearing. Then we use a psychophysiological interaction analysis called PPI, where you look for task-specific increase in relationship between brain regions. So it's not just one response, but it's a network of response. And what we find is if we compare original music versus tempo-modified music, the music group clearly responds with a network that includes, so the seed is put into the auditory cortex because that's where the sound is heard, but then it leads to these activations in different parts of the brain, the middle cingulate, for example, also a little bit of motor activation, and especially also caudate and putamen. And there is absolutely no significant results if you do that comparison in the non-music or in the term group. So there doesn't seem to be a proof of sort of an innate ability to detect temporal changes on a network basis in non-exposed newborns. We did that also looking at music versus non-music group, and then looking how is the contrast between original versus tempo modified different, and you again find with this different analysis exactly those areas that we found before. So there's clearly a proof of concept in that. We look at that also music versus term group. So for example, how do they different? And you see that the music group also has a much better, much more developed network response than the full term group. So if we do the further analysis, those are the rest of the comparisons which do not give any response of the network. We can say that these findings suggest a task-specific increase in favor of the preterm music group when listening to trained original music. The areas that they activate very much links to what you activate in the brain if you listen to familiar music versus non-familiar music in adults. And clearly these newborns that heard this music have been able to modify their network so to respond to that original tune. So in conclusion, we can say that these sensitive periods in neural development seems to be for both language and music exposure change the neural processing preterm infants. They can learn tempo and melody discrimination, which is not present per se in full-term non-trained newborns. And so really when we design NICU environment intervention, we should be aware of what kind of connectivity changes we can do. And of course, we don't know yet if they are long-term beneficial. So just a few words, you heard that, so I don't have to go over it. The developmental consequences of noise. There were early studies where we showed that especially the prefrontal cortex networks were very much influenced by a more environmental care-oriented care, for example, NIDCAP, which of course also includes the talking mother, and that had those structural changes also had functional consequences. So when we look at that in the resting state, so we can assume found that these kind of interventions change the basis of how our brain connects to each other, the regions connect to each other. And when you do these resting state analysis, you can define specific networks. And those are the ones that are generally observed. So these regions sort of work together. And one of them is the salience network. By the way, the first ones who described these resting state networks in newborns were from Karolinska. So they have a long tradition in that, since, of course, there are many other groups that have described this resting state. And these resting states can be perturbed by painful procedures. Here, for example, we looked at the PKU test in the before and after in the MRI, and we can see that it's the modulation of the orbitofrontal networks resting state by this painful process. And low and high stress influenced that, and what we've particularly found was that these salience networks, so the network between that sort of controls the state and the perception of the infant, is very much changed in preterm versus term infants. So this salience detection is considered to be a key mechanism that facilitates learning and to extract the pertinent part of perception. And it's altered in preterm infants, still in adults, and it's linked to synaptic gene expression in these networks. And what we find is that this music experience over this time period particularly improves this salience network. And so in some analysis where we again compared the full term and the preterm with music and the preterm without music, we can see that there are particular network accordances and discordances where the preterm without music has a lot of differences compared to the full term, whereas the music one has a much reduced, so we move the resting state connectivity, functional connectivity of the preterm more towards the distribution of accordance and discordance in that we observe in the term. And this is particularly true again for these salience networks that are heavily altered in the preterm without music. So in that, I think we still need to learn a lot on how we can improve quality of life long-term for ex-preterm infants. But clearly, when we say music, emotionally nurturing environment might produce more capable learners. And so I thank, of course, all my PhD students and nurses and experts in music like Didier Grandjean that helped in designing this research. And I would invite you to come this fall to Paris and discuss with us more about developmental care and early interventions to improve development. Thank you very much.